Okay, welcome back everyone. In this segment, we're going to be talking about how the laws of gravity led to Kepler's laws of planetary motion. So we're going to be talking about what they are and how we can use them to predict the motion of celestial objects. Okay, so actually there's a little bit of a backstory about Kepler's laws, and the very short version of it is that there's this dude, Tycho Brahe, who was very famous and well-known in Denmark. He basically had his own observatory built for him by the king, but he was taking very precise data and doing wrong stuff with it. For example, he was trying to show that his data led to a geocentric universe with the sun at the center, which we know now is an incorrect description. And actually they knew it back then, but he was holding on to this because he was kind of stubborn and he was smart, but he was going in the wrong direction. Okay, so basically what happened is that he had an assistant by the name of Johannes Kepler, who was very well trained in mathematics. He was brilliant, and he wanted access to this data that Tycho Brahe had, but couldn't have access to it because Tycho was kind of a jerk. So as the story goes, there was a big banquet and Tycho maybe had too much to drink, and for one reason or another, as the story goes, his bladder burst and he died a horrible, painful death. And then later on, nobody could find Johannes Kepler or the data. So the theory is that he grabbed the data and he ran. And there's actually a lot of evidence that Tycho died from mercury poisoning. So anyways, this may or may not be 100% true, but it's kind of an interesting story. So Kepler basically took this data and ran with it, literally, and he came up with 3 laws of planetary motion. So the first one is that each planet moves in an elliptical orbit with the sun at one focus of the ellipse. And we'll break each of these down one by one. Second, a line from the sun to a given planet sweeps out equal areas in equal times. And we actually started to look at this when we did angular momentum last unit. Finally, the periods of the planets are proportional to the 3/2 powers of the major axis lengths of their orbits. And we saw this earlier, that t is proportional to r to the 3/2. So we'll be talking more about this. Okay, so for the first law, basically Kepler said that all orbits are ellipses and that the sun is at one focus. So what's at the other focus? Turns out that it's empty space, except if you have something like the Earth's orbit, where the two foci are so close together that they're essentially inside of the sun. Okay, now the second law gets a little bit more complex. And the second law, what we want to show is that these two areas here and here are actually the same in an equal amount of time. So we're going to break this down. So take a look at the diagram labeled B here, which shows one of these sectors and a point on the sector with the actual velocity v and the perpendicular component of that v sine phi. So phi is the angle between r and v. Okay, so if we were calculating momentum and we needed to do L equals r cross p, right? That would be equal to rp sine of that angle phi. Okay? We also have on this diagram a small angle d theta that the planet travels through in a small period of time, dt. And so it's going to sweep out an area dA. Okay? And we also have this small segment r d theta, which is kind of perpendicular to r. So the first thing to note is that the area of this shaded triangle dA is 1/2 times the base, which is r d theta, times the height, which is r. So hopefully that makes sense. Okay, so dA dt if we take a time derivative, is 1/2 r squared, because of these two r's, d theta dt. So we just, take the derivative of each side with respect to time. But another way to write it is to say, let's say that v perpendicular is equal to v sine of phi, and so therefore ds is equal to r d theta, because remember s is equal to r times theta, so ds is r d theta. So another way to write this is that v perpendicular is equal to essentially ds dt. Okay, so that's another way to write this perpendicular velocity here. And the reason that we bring this up is because we have an r d theta dt up here. Okay, so another way to write dA dt is to say that it's equal to 1/2 rv sine phi. So pause if you need to, because this is a little bit tricky, but basically what we're saying is that 1/2 r squared d theta dt is equal to 1/2 r times r d theta dt, which is v perpendicular, and v perpendicular is v sine phi. Okay, so that's where this comes from. Okay, so where do we go with this? Well, what do we do with this? First of all, we note that rv sine phi is the magnitude of basically 1/m times the angular momentum, because that's r cross v times 1/m. So we were just missing an m here, so if we sort of factor that out, okay, then we can do something with this, okay? So we rewrite dA dt as 1/m, the magnitude of r cross mv, which is equal to L over 2m. And just as a reminder, what we had was that dA dt was equal to 1/2 rv sine of phi. And so if we stick an m in there and then multiply that by 1/m, okay, this right here is going to get us our angular momentum, r cross mv, and then we have a 1/2m that's sitting outside. So we have L over 2m is equal to dA dt. So the change in this area per unit time is equal to the angular momentum divided by 2m. But we want to prove that dA dt is constant, and it's only going to be constant if the angular momentum L is also constant. Okay, so how do we show that that's true? Well, if this is the sun and this is the planet, okay, then the planet has a force Fg directed inwards, but the radius is directed outwards. Now, since Fg is basically parallel to r, anti-parallel, okay, the torque is 0 from the force of gravity. And since torque is equal to 0, we learned last unit in rotation that a net torque is equal to a change in angular momentum over time. So therefore, dL is equal to 0 and L is constant. So because of this, okay, dL dt is equal to torque, which is r cross F, which is 0. And so therefore we have proved out what we set to, which is that L is constant. So therefore dA dt is constant. And planets sweep out equal areas in equal times. So this was a really big realization for Kepler. It was kind of cool. Okay. So his third law said that basically r cubed and t squared had a relationship. All right, and what we want to do is we want to start with Newton's second law for circular motion. So the force of gravity is the centripetal force. Whoops. Let's Let's call that a C. So G, and we'll just call our two masses big M and little m over r squared is equal to little m v squared over r. Those cancel. Now I'm not going to cancel this r because I'm going to substitute that v is equal to 2 pi r over t, and we alluded to this earlier. Okay, so that's going to be 2 pi r over t squared over r, which is going to be 4 pi squared r over t squared. So we have gm over r squared is equal to 4 pi squared r over t squared. And then we can rewrite this as gm over 4 pi squared is equal to r cubed over t squared. And this is the usual formulation of Kepler's third law, which is basically to say that r cubed over t squared is equal to a constant. And this constant depends on the mass of the object that you are orbiting. Okay? And so for the sun, this is the so-called Kepler constant, would be g mass of the sun over 4 pi squared. That 4 is terrible. That's better. Okay? Now, there's one cute thing that you can do here. Okay? So if m is the sun, okay, and if you write r in a special unit called astronomical units, which is abbreviated AU, and also if t is measured in years, if all of these things are true, then basically gm over 4 pi squared, which is equal to r cubed over t squared, is equal to 1. So this is a special case of Kepler's law. Now the astronomical unit is basically the r from the sun to the earth. It's 150 million kilometers, but that number isn't important. The important thing is that, well, how far is the sun to the earth? It's 1 AU, so if I plug in 1 cubed over 1 squared, I better get 1. So that's just a nifty thing to do with Kepler's third law. Okay, so one quick example. We want to find the period of orbit for a satellite at an altitude of 25 kilometers above Earth's surface. So we just use r cubed over t squared is equal to gm over 4 pi r squared. And in this case, this big M has to be the Earth. So you always want to use the mass of whatever you are orbiting. Okay? So we can rearrange this for the period. And so just a little bit of algebra. So 4 pi squared r cubed over g mass of Earth. And that's going to give us a time of about 5,100 seconds, which is about 85 minutes. So for low flying orbits, so 25 kilometers would be pretty low, it only takes about an hour and a half for something to go around the Earth, which is kind of crazy because that's really fast. Okay, so next time we're going to talk about spherical mass distributions, and we're going to introduce a very important concept called Gauss's law.